Hello, Calc BC. Today we're going to be starting lesson 3.2. This is integration part 2. Today we're going to be talking specifically about the second fundamental theorem of calculus and then kind of digging deep into definite integrals and talking about natural logs for derivatives and integrals. So you can see on your screen right now we have the course and exam description from College Board as always. And this whole unit is going to be covering their units 6, 7, and 8. Today is going to be a deep dive into specifically some lessons in their unit 6. So we're going to be talking about applying properties of definite integrals, fundamental theorem of calculus and definite integrals, antiderivatives and indefinite integrals, and potentially even some use substitution that we're going to continue from yesterday or whenever you did 3.1. All right, so I'm going to pause this and then I'll pull out the notes. All right, so here we go. I also just realized I was wearing my mask when I was recording, and I did not need to do that because I'm the only one in the room. Let me just kind of make this a little bit bigger here. I don't think it's going to change what you see, but it will help me. Okay, here we go. So again, here's lesson 3.2. We're going to get started. So example 1. Evaluate the given definite integrals. So if you take a look here, we're going from 0 to pi over 6 sine of 3x dx. And we're going to do this using our integration rules. This is technically a u substitution style question. We could say that u is 3x. So du is going to be 3 dx. And what that means is that I should rewrite this question with a 1/3 in front like this. So I'm going to do 1/3 from 0 to pi over 6 sine of 3x times 3 dx. So you can see I have the 1/3 here and the 3 here. Those will cancel out to give us the original. And now I'm going to plug in. So when I plug in here, I have 1/3 sine of u du. And notice that I didn't write the endpoints of the integral yet, because whenever I do u substitution, I want to change the endpoints to be in terms of u instead of in terms of x, because now we're integrating in terms of u instead of an x. So let's think that through for a second. All I have to do is plug those in for x here and see what we get. So for the first one, we have 0. So I'm plugging in 0 for x, 3 times 0. And so u is still 0. For pi over 6, I'm going to plug that in here. So 3 times pi over 6 will be 3 pi over 6, which is pi over 2. And now we have our integration in terms of u fully. So we're going to be able to do this. And so we're going to have 1/3. Remember, Santa Claus, negative Santa, negative Claus. So the integral of sine flips back to negative cosine. So we're going to have cosine of u, negative in front. And after we take the integral and we have a definite integral with bounds, we usually put like a straight up and down line on the right end of our result and say that we're evaluating from 0 to pi over 2. And here's the cool thing about this. When we are evaluating u substitution and we have bounds, we have definite integrals, we don't need to change back to x. Now that we've already changed our endpoints, we can just plug them in. So how that will work is we take this whole thing and we plug in pi over 2 minus this whole thing plugging in 0. So we're going to have negative 1/3 cosine of pi over 2 minus negative 1/3 cosine of 0. Just like that. And we can go further because we can evaluate this. Negative 1/3, the cosine of pi over 2 is the x value, and it's going to be 0, comma 1, so that's going to be 0, minus negative 1/3 cosine of 0, which is the x value at 0, which is 1 comma 0, so it's 1. So now we have 0 minus negative 1/3, which is going to be positive 1/3. And that means that if we actually graphed sine of 3x and we shaded in the area from an x value of 0 to an x value of pi over 6, and if we could somehow figure out the area, it would be 1/3 units, 1/3 units squared. All right? So that's how we do a definite integral algebraically. Let's try this again in letter B. This time, I can see we have a composition of functions over here. The sine of 5x is to the 3rd power. So I'm going to let u equal the sine of 5x. And du will be the derivative, which is going to be cosine of 5x times 5, because we multiply by the derivative of the inside. And so let's see if we can translate this here. So we have sine of 5x is cubed. So we're going to have u cubed cosine of 5x becomes the du, but we needed to have a 5 here, so I'm putting a 1/5 in front. Okay? We can rewrite that in the original if we wanted. There's a 5 here and a 1/5 here, so that we can actually cancel that out and get du. And I need the bounds, though, of my integral. So I got to plug both 0 and pi over 20 in for x right here. So if I do sine of 5 times 0, it's going to be sine of 0, which is 0, the y value of the ordered pair on the unit circle at 0, an angle of 0. Pi over 20 I plug in here. I get 5 times pi over 20, which is pi over 4. And so we're doing sine of pi over 4. And if you think about your unit circle, pi over 4 is at root 2 over 2, root 2 over 2. So the y value is root 2 over 2. Okay, so we are ready to integrate. So we have 1/5 times u to the 4th over 4. And that's going to be evaluated from 0 to root 2 over 2. And so we can plug in for u. I could also, before I do that, if I wanted, I could combine this to make it u to the 4th over 20 from 0 to root 2 over 2. So it's going to be, in other words, 1 over 20 times root 2 over 2 to the 4th minus 0 to the 4th. I just pulled the 1/20th out in front so I wouldn't have to write it 2 different times. This is quantity to the 4th. So what are we going to get there? We're going to get 1 over 20 times root 2 to the 4th is going to be root 2 times root 2 is 2. And then another 2, so 2 times 2 is 4. And 2 to the 4th is 16 minus 0. So I'm getting, if I multiply that together, I'm going to end up with 1 over 80. Boom. A little bit more complicated, but that's how we do a definite integral with bounds and with u substitution. So there you go. Let's take a look at the next section. The second fundamental theorem involves taking the derivative of an integral. Try the following problems and see if you can discover what the theorem says. So we're going to do this together. And notice that for each of these, we have an integral from some number to x. And then we're going to be taking the integral first and then taking the derivative of the result. So for this first one, let's try it. So we don't have to do any sort of u substitution here. We're just going to be doing the integral first. So we're going to be taking the derivative of from t squared. If we integrate that, we're going to get t cubed over 3, We have to evaluate that from 1 to x. And so we're going to end up with x cubed over 3 minus 1 cubed over 3. In other words, 1/3. And then we take the derivative of that. So we're going to end up with 3x squared over 3, which will just be x squared, minus 0. So there's our derivative of our integral. And let's try the second one. Same process. So first we're going to take the integral of cosine t, which is sine t. We're going to do that from pi over 6 to x. And so we'll write that out. It'll be sine x minus sine of pi over 6. And then we take the derivative. So the derivative of sine we know is cosine. And we could actually evaluate sine of pi over 6, but it doesn't matter because we know it's a number, and any constant, when we pass it through a derivative, it equals 0. So it's going to go away anyway, and we're going to be left with cosine x. All right, so that leads us to the theorem, because if you look at both of these questions, what you'll notice is the upper bound of the integral, which was x, was replaced t, and that's all that happened in the final answer. So for this derivative, all we need to do, if we're going from a to x of f of t, and then we're taking the derivative, the answer is always just f of x. We plug in x for t. Okay. So that's the rule. We can say something, we're going to see what happens if the x is the lower bound instead of the upper bound. So we're going to try that next. So let's try this. We're going to do the same thing again. And this is kind of a mirrored version of the first example up here, but let's try this. So we're going to be taking the integral of t squared, which again is t cubed over 3. We're going to go from x to 4 this time, which is going to look like this. And we'll have 4 cubed over 3 minus x cubed over 3. When we take the derivative, that first term is a constant, so it's going to be 0 minus 3x squared over 3, which is x squared. So we get negative x squared. So all that means is that if the x is the lower bound instead of the upper bound, and the upper bound is just a constant, and we're taking the derivative of the integral, the answer is going to be negative f of x. As you see, t squared became negative x squared. It's just like if you flip the bounds of your integral. We had a property last lesson that said that it's just negative of the regular integral with the bounds flipped. So let's try this one now. So now we have an x squared as the upper bound instead of an x, and we're going to see what happens here. We're going to do this one by hand and then write the actual theorem so that we won't have to do it by hand every time. So for this one, we're going to start the same way we did before. We're going to start with the derivative by writing derivative of, and then we'll take the integral of cosine. So the integral of cosine is sine, so it's going to be sine of t, evaluated from pi over 6 to x squared. And that's going to be, when we plug in our values, it'll be sine of x squared minus sine of pi over 6. And remember, sine of x squared is different than sine squared x. Sine squared x means the whole sine x is what is squared. In this version, just the x is squared, then we take the sine. So it's kind of like switching the order of operations there. And let's take the derivative. So the derivative this time is going to be cosine of x squared times the derivative of the inside, which is 2x. And this part's a constant, so it goes away. So we end up with this, which is slightly different, right? It's not as simple as just taking the x squared and plugging it in for t. Now we also had to multiply by the derivative of the inside. So the official second fundamental theorem of calculus, with the chain rule included, looks like this. If we're going from a, some constant, to g of x, some x expression, the solution is f of, instead of f of t, we're plugging in the g of x. And then we're multiplying by the derivative of g of x. All right, so we can use that to evaluate instead of going all the way back through to the original integral and derivative like we were doing before. In this first one, that means all we have to do is plug in x. The derivative of x is just 1. It's like the earlier questions that we were doing. So this is the derivative of an integral, and all we do is plug in x for t. Done. In this one, it's also to x, so all we do is plug in x for t. Done. We have a couple more examples. These ones will use the chain rule. In this first one, we have 1 over 1 plus t from -1 to x cubed, but then a derivative. So all we do is we plug in x cubed for t. But then we have to multiply by the derivative of x cubed. And up here, we're going to do the same thing. We're going to plug in sine of x for t. And notice the t was squared. So this is going to be sine squared x, like that. And then we multiply by the derivative of sine. Boom, that's it, okay? So even though this was sine squared, we don't have to do the derivative of sine squared because the original bound of the integral was sine x. That's what we take the derivative of out here. Let's keep going. The rest of this page is one big example. Functions defined by integrals. Let's take a look. The graph of a function f consists of a quarter circle right here and several line segments here, here, and here. So it's telling us those are straight lines, and this is an exact quarter circle. Let g be the function given by g of x equals the integral from 0 to x of f of t dt. So the first thing we want to do is find g of 0, g of -1, g of 2, and g of 5. Let's try that. So if we are finding g of 0, think about what that means when we plug it into this integral. It means we're plugging in that 0 for x. So it's going to be from 0 to 0, f of t dt. And we know that any integral, if the upper and the lower bound are the same, it equals 0. For g of -1, it's going to be the integral from 0 to -1 of f of t dt. And if we take a look at the graph, from 0 to -1, that's backwards. So we could write it as the negative integral from -1 to 0. So we're going to be finding, this is the graph of f. So we're finding the integral from -1 to 0 of f. So the area under this curve, this is a triangle right here. It has a base of 1 and a height of 2. So 1/2 times 1 times 2 is going to be 1. And it is a negative because we had to flip the bounds. So it's -1. Then we want to also find g of 2 and g of 5. All right, I'm not going to write the integral each time for these ones, but let's take a look. Remember, we're going from 0 to 2 this time. So from 0 to 2, we have that quarter circle that we were talking about there. And we want the area of the quarter circle. This circle has a radius of 2, because think about that the center point of the circle is right here at the origin. So we're going to be doing pi r squared, but only a quarter of it. It's going to be 1/4 of pi times 2 squared, because the radius is 2. So it's 1/4 because we're doing a quarter of the circle. Pi r squared is the area of the whole circle. The radius is 2. So 2 squared is 4 times a fourth is 1. So this is really just pi. And you can kind of see that if you think pi, we know is 3.14 ... and think about the area or how many squares we could fit inside of this. Kind of makes sense that it could be 3.1 something if you rearrange the squares that are visible in there. So that makes sense. G of 5 is going to be the area from 0 to 5. So from 0 all the way to 1, 2, 3, 4, 5. So we're going to start with the pi. And then this region down here has to be included. Let's see, what do we got here? We've got 1 square, 2 squares, and then this is a triangle with area 1, and this is a triangle with area 1. So we have minus 4 because those are below the x-axis, and pi minus 4 is good enough. So we've got the area. All right? Okay. So now we're going to answer some more questions about how f relates to g. And so it's going to be helpful, and this is true for any time that you're doing this type of question for a free response on a quiz or on the AP test. We want to write how this graph is related, how f and g are related. So we know that g of x equals the integral from 0 to x of f of t dt. That means that g prime is going to be the derivative of that. Now think about what we've been doing this whole lesson so far. The derivative of the integral, it just means we're going to plug x in for t. So g prime is equal to f. We're also going to have some questions about the second derivative. So we're going to write that g double prime equals f prime. And now, because we've written this, we can use that to justify our answers in all of these questions. So let's take a look. In letter B, on what intervals is the graph of g increasing? So to tell if something's increasing, we look at the first derivative, which in this case is f of x. So here's our graph of f of x. And we're going to be, the original function is going to be increasing when the first derivative is greater than 0, right? So it's going to be when g prime is greater than 0, which means that f of x is greater than 0, right? Because when we're greater than 0, that's when we have a positive slope on the original function. So when f of x is greater than 0, that is from -1 to 2. That is the interval in which the graph g is increasing. Find all values of x on the open interval from -1 to 5, at which g has a relative maximum. So a relative maximum occurs at a critical number, and so that's going to be when g prime equals 0, and a max occurs when the sign changes, right? And a max occurs when the sign changes from positive to negative. So on the graph.
Please excuse me for the interruption.
All right, sorry for that interruption. We'll keep going. So we're looking for when g prime equals 0 and sign changes from positive to negative. That's going to tell us when we have a relative maximum on the original graph. Remember, our g prime is f. So we can look at this graph. When does the graph equal 0 and change sign from positive to negative? That happens right here at x equals 2. For letter D, we're going to find the absolute minimum value on the interval -1 to 5 on the graph of g and the value at which it occurs. So we already found several values on the graph of g, but let's think about our critical numbers where we should be checking. If we were going to make a chart for the candidates test, we would want to check the endpoints, -1 and 5, and we would want to check any critical numbers. We only have one critical number where the sign changes direction, and that is at 2. So -1, 2, and 5. We already found all of those values. So we know that at -1, we're at a y value of -1. At 2, we're at a y value of pi. And at 5, we're at a y value of pi minus 4. So the question is, which of these values is lowest? Pi minus 4, so pi is 3.14. We subtract 4 from that, it's going to be something between 0 and -1. And -1's smaller than that. So the x value is -1. So the minimum value is -1 at x equals -1. And we found it right there. Letter E, on what intervals is the graph of G concave up? So we know that concave up means that the second derivative is positive. So we're looking for when the second derivative is greater than 0, which in our language means that the first derivative of f is greater than 0. And so we're looking at this graph. We want the first derivative of this graph to be positive. So in other words, we want the slope of this graph to be positive. We want this graph to be increasing. And that happens from -1 to 0. And from 3 to 5. And finally, letter F, find the x coordinate of each point of inflection of the graph of G. Okay, so we're back to G, points of inflection. For G, if we're thinking in terms of G, it means that G double prime of some value equals 0, or G double prime of C does not exist, and G double prime changes sign. In our language or in our graph, that means F prime. And so we know that G double prime equals F prime. So we're going to be looking at our graph and looking for when the derivative of this graph equals 0 or doesn't exist. So the potential options are x equals 0, we have a corner. So that's going to have a derivative that doesn't exist. We also have a corner at x equals 2 and at x equals 3. There's actually no points with a horizontal tangent. It's just 3 corners. And now we need to check, does our sign change at these points? So does the graph of this function f change from increasing to decreasing or change from decreasing to increasing? At this point, you can see we change from increasing to decreasing. So that is indeed going to be a point of inflection. So that changes from increasing to decreasing, which means the second derivative is going to change from positive to negative. X equals 2 is decreasing to decreasing. So we can actually cross that one off. It does not change sign. And then for x equals 3, we change from decreasing to increasing. So that one does count. So there's our 2 points of inflection. All right, we're going to keep going. Next example, given this function, for what values of x is the graph of f decreasing? So we know how to find if a function is decreasing. We're going to take the first derivative first. And this is an integral from a value to x. So we know all we have to do is plug in x for t. And that's our first derivative. And we want to know for what values is this graph decreasing. So we're going to set it equal to 0. Find the critical numbers. So we got -2 and 3, and we're going to set up a sign chart for f prime. Because if f prime is less than 0, that's when f is decreasing. We know that. So we have the numbers -2 and 3 on our sign chart. If we plug in a value lower than -2, for example, -3, we're going to end up with a negative here and a negative here. So it's a negative times a negative times a negative. That's going to be negative. If we plug in a number like 0, we're going to get a positive times a negative times a negative. So that's going to be positive. And if we plug a number like 4, positive, positive, positive. So that's going to be positive. And so when was our first derivative less than 0? It was from -infinity to -2. All right. So there's that one. Let's keep going. Suppose that 3x squared minus 12 equals the integral from c to x of f of t dt. Very interesting, very interesting. So the first question here is, what is f of x? This question's a little backwards from normal, but think about this. How does this equation relate to f of x? Well, over here we have an integral from c to x of f of t. We know that if we take the derivative of this, we're going to get f of x, right? So that right side really equals f of x if we take the derivative. So if we take the derivative of the right side, it should be equal to the derivative of the left side, right? So the derivative of the left side is 6x minus 0. So f of x equals 6x. We found it. So now part B, find the value of c. Interesting, interesting. So we originally had 3x squared minus 12 equals the integral from c to x of f of t dt. We know that f of x is 6x. So if f of x equals 6x, f of t equals 6t, right? It's just replacing the x with t. So we can replace this integral with 6t. And in that way, we can actually integrate this. So this is kind of a weird question, but we can do this. So we got 6t dt, so we're going to integrate that, and we end up with t squared over 2. Which is going to become 3t squared, right? Because if we do t squared over 2, the 6 over 2 becomes 3. And we're doing that from c to x. So we're going to end up with 3x squared minus 12 equals 3x squared minus 3c squared. Because I plugged the x in for t and then I plugged the c in for t and subtracted. And now we're going to try to solve this for c. So the 3x squareds cancel. If I subtract 3x squared from both sides, I will end up with -12 equals -3c squared. Divide by -3, and I get 4 equals c squared. Square root both sides, and I get plus or minus 2 equals c. Kind of weird, but we could do it, right? Yeah, look back over that problem or replay this part of the video if that didn't quite make sense. Moving on, given that the integral from -2 to 5 of f of x dx is 4, find the integral from -2 to 5 of 3 times f of x minus 2 dx. All right, so what we're going to do now is our integral properties, being able to split one integral into multiple integrals. So this really equals from -2 to 5, 3 f of x dx minus the integral from -2 to 5 of 2 dx, right? I can separate two terms into two different integrals with a minus in between, just like the original. I can also pull a constant multiplied by a function out in front of the integral. So I'm going to do that in the next step. So I'm going to have 3 integral from -2 to 5 f of x dx minus negative 2 to 5 of 2 dx. Okay? And now I know that the integral from negative 2 to 5 of f of x dx is 4. So that's pretty nice. This first part just becomes 3 times 4. I didn't even have to integrate. The second part, though, I would think about that the integral of 2 is 2x. And we're going to evaluate that from negative 2 to 5. So now we have 12 minus parentheses 2 times 5 minus 2 times negative 2, which is 12 minus 10 plus 4. So 12 minus 14 is negative 2. It's really easy to accidentally just subtract 2 from your integral here instead of actually following through, turning this into 2x, and then finding the integral. You might also think about that this is representing a horizontal line at 2. And if we're going from negative 2 to 5, that's creating a rectangle that has a length of 7 units from negative 2 to 5 and a height of 2. So 7 times 2 is giving us this 14 that we have in these parentheses. But if you're not really a visual person, the integral works just as well, like we wrote down. Next question. Now we have a piecewise, and we're evaluating from negative 3 to 2 of f of x dx. Since this first chunk of the piecewise is valid for a domain or x values of less than or equal to 0, and the second chunk is for x is greater than 0, what I'm going to do is separate this integral into 2 pieces, and we're going to go from negative 3 to 0 f of x dx plus from 0 to 2 f of x dx. And in our next step, I'm going to plug in the function. Now from negative 3 to 0, this x squared plus 1 doesn't really matter, right? We only care about the x plus 1 for that part. So it's going to be negative 3 to 0, x plus 1 dx plus from 0 to 2, now we have the x squared plus 1. And so I'm going to integrate both chunks. So we have x squared over 2 plus x from negative 3 to 0 plus x cubed over 3 plus x from 0 to 2. So we're going to have, if we plug in 0 as our upper bound, that's going to just equal 0 minus negative 3 as our lower bound. So we're going to have negative 3 squared over 2 plus negative 3 plus, now 2 is our upper bound, 2 cubed over 3 plus 2 minus, if we plug in 0 again for this one, we're going to end up with 0. So now we just have to kind of simplify this. So we have negative 3 squared is 9, so 9 halves minus 3 plus 2 cubed is 8, so we have 8 thirds plus 2. And so if you add all of those together, find a common denominator, you're going to end up with 19 over 6. There we go. That's how you do that question. All right. So that's a nice overview of definite integrals, the second fundamental theorem. And what we're going to do now is just kind of backtrack for a second and think about the natural log function, ln. And we'll talk about derivatives and integrals of the natural log function, since we haven't really covered that yet. So the natural log function is defined by ln of x, which is the integral from 1 to x of 1 over t dt. You may remember from calculus AB that the derivative of natural log is 1 over x. So this is kind of showing you that natural log is the integral of 1 over t, which is the same thing. And you can kind of read over some of this if you want. We have just the base information about natural logs. See what I did there? Base. The base of natural logs is the number e. E was named for a Swiss mathematician, Leonard Euler. So we've got E, which is 2.7183. It has a limit in its definition. If you're interested in that, you can read over that. And we're going to do a rough sketch of the graph here, which looks like this. That's our natural log of x graph. The domain is from 0 to infinity, exclusive, not including the 0. And the range is from negative infinity to infinity. So all real numbers are included for y values. Function is continuous, increasing, and one-to-one, and it's also concave down for the entirety of the graph. Other properties. If a and b are positive numbers and n is rational, then the natural log of 1 is 0. So this is at an x value of 1. The natural log of e is 1. So wherever e is, 2.7 has a y value of 1. And we can also separate natural logs that have numbers multiplied inside into two things added. We can separate two things that are divided into two things subtracted. And any exponent that's on some term a inside of a natural log can also be moved out in front as a coefficient, and it's still equal. So the first part is just a review from pre-calc and potentially even from algebra 2 of how you kind of expand and condense logarithms, specifically natural logs, which are called ln. Excuse me. So for this first one, write as a sum, difference, or multiple of log. So the first thing I see here is that we have division. So I'm going to separate this into two natural logs that are subtracted. So this will be natural log of x squared plus 3 squared minus the natural log of the cube root of x squared plus 1. And for the last step, I'm just going to kind of fully expand, which means that I'm going to write the exponents as coefficients. So the 2 exponent comes in front. And this cube root, you can think of that as a 1/3 exponent, which can come in front. Notice that I can't separate these anymore. Even though there's two terms inside of this natural log, I don't have any properties for if there's two terms added inside of a natural log. We can separate when there's two things multiplied into addition, but if there's two things added, we're stuck. So that's our fully expanded form. In this second example, we're going to write something expanded as a single log. So the first thing we're going to do is move the coefficients to exponents. And the 1/2 is going to become a square root. And since these are added, I can combine this into one natural log that's multiplied. So it's going to be x plus 3 squared times the square root of x minus 2. And that's technically a valid answer. So that's all of this written as one single natural logarithm. All right, so we're going to keep going here. Now we have this property, as we saw above, that the derivative of the natural log is 1/u. And so let's try this. In this first question, we have the natural log of 2x. So the first derivative is going to be 1/2x. But don't forget, we technically have to think about the chain rule. So if there's 2x inside, we have to multiply by the derivative of the inside. So this is going to be multiplied by 2, which you can think of as 2/2x, which just reduces to 1/x. In the second one, same idea. We're going to get 1/x squared plus 1. And we're going to multiply by the derivative of x squared plus 1, which is going to be times 2x. So we can write this as 2x over x squared plus 1. Okay? We're going to do a couple more examples here and before we get into integrals. So let me flip the page. All right. So x times natural log of x. Now this is our product rule, right? So we've got u is x and v is natural log of x. So our first derivative is going to be u times the derivative of v plus v times the derivative of u. And x times 1 over x is going to be 1 plus natural log of x. In the second one, we have the natural log of the square root of x plus 1. So I'm going to think of that as the natural log of x plus 1 to the 1/2. So when we take the derivative, just like before, we do 1 over the inside, x plus 1 to the 1/2, times the derivative, which is going to be 1/2 x plus 1 to the negative 1/2, times the derivative of x plus 1, which is just 1. And so now we have, let's see, the 1/2 needs to stay there. The x plus 1 to the negative 1/2 should be moved to the bottom. It's going to end up multiplying these x plus 1s together. So we can add the exponents and it becomes just x plus 1 to the first power. So we have 1 over 2 times x plus 1. Now, an alternative way of solving that one, if you think about our logarithm properties from the previous page, we can move this 1/2 power out in front like this. And then if you take the derivative, we have 1/2 times the derivative of natural log of x plus 1, which is 1 over x plus 1, times the derivative of the inside, which is 1. And boom, we got the same thing. That equals 1 over 2 times x plus 1. So your choice how you want to do that. It's the same answer either way. What about something like this? The natural log of the natural log of x. So we're going to do the same thing as before. So this is our initial inside. So we do 1 over that times the derivative of the inside, and the derivative of the natural log of x is 1 over x. So this combined is 1 over x times natural log of x. Next question, what about if it's the natural log of x quantity cubed? Right, so we've got to go through a whole chain rule. So first we do 3 times the natural log of x squared. Then we multiply by the derivative of the inside. And the derivative of the natural log of x is 1 over x. So if we wanted to combine this into one fraction, it would look like this. Please note that this is not the same thing as saying that the x is cubed inside of the natural log. So we actually can't move this 3 in front. If we move the 3 in front, it's a totally different expression, right? Where was the last one where we had an exponent? Well, if we just look at the original rule, the a to the n is inside of the natural log. It's not natural log of a quantity to the nth power. It's natural log of a to the n. So when you see it written like this, that's something totally different. We can't use that property to move the 3 in front. When we take the derivative, now we're doing the chain rule. So we do bring the 3 in front because that's part of the chain rule, power rule. 3 natural log x to the second power because we subtract 1. And then we keep going. All right, last one. Now, okay, well, I could have, I guess, just looked at the next example. This one can be written as 3 natural log of x. And I think we should consider it that way for when we're taking the derivative. It's going to make it a lot easier. So now we do the derivative. It's 3 times the derivative of natural log of x, which is 1 over x, or we just get 3 over x. Okay. And that brings us to integration. So in the previous section, we talked about that the derivative is 1 over u. This corresponding integration formula is that the integral of 1 over u du is the natural log of the absolute value of u plus c. These absolute value bars are important when we're integrating, and we need to make sure that we remember that. We always want to write that so that our statement is true. That's because the negative numbers, you can't take the natural log of a negative number. If we take a look at that graph, the domain doesn't have any negative numbers. There's nothing over here. So we're going to have errors if we don't include this absolute value bar. So let's take a look at this first one. I would rewrite this as 2 integral of 1 over x dx. So you can see clearly that this expression with the integral here is exactly coming from here. So we can write this as 2 ln of the absolute value of x plus c. Now, I talked about this last lesson, but we don't have to distribute the 2 to the c because c just represents a constant. It's any real number. And if we multiply something by 2, it's still going to be any real number. It didn't change the fact that this is just a constant representing any value. So we don't have to write 2c or anything like that. Let's keep going. Okay, what about if it's a definite integral from 1 to e of 2 over x? So I'm going to start out by pulling out the 2, just like in the previous question. And now we know that we have integral of the natural log of x in absolute value. And we're going to evaluate that from 1 to e. So far I've always been using one straight up and down line to represent kind of the bounds of the expression. Another way of doing that is if you have kind of square brackets and you write the bounds to the right like this, it means the same thing. And let's see, what am I doing here? So I'm going to keep the 2 out this time, and I'm going to plug in the natural log of e minus the natural log of 1. I don't need the absolute value bars anymore because e and 1 are both positive already. So the absolute value of e is just e, and the absolute value of 1 is just 1. So if I think this through, natural log of e is 1, and the natural log of 1 is 0. So we have 2 times 1, which is 2. Next question. So in this one, I am going to let u equal 2x minus 1. So du is going to equal 2 dx. And so when I plug in here, I'm going to have, first I'm going to set it up with the 1/2 and the 2. So I'm going to pull 1/2 in front and multiply by 2 on the inside. Those will cancel out to get me the original integral. And so now I have 1/2 the integral of 1 over u du. And so that's going to equal, well, 1/2 natural log of the absolute value of u plus c. And if I plug u back in, I'll get 1/2 times the natural log of the absolute value of 2x minus 1 plus c. Right? Because this is an indefinite integral, it doesn't have bounds, so we have to plug u back in for the final answer. So that our final answer is in terms of x, just like the original question. All right. There are 1, 2, 3, 4, 5, 6 more examples. These examples are going to practice integration with natural log. And I could spend several minutes of your time writing it all out, but instead what I'm going to do is just show you my work. So what I'd like you to do is, if you haven't already, open up the PDF of this notes lesson and try these examples, and then come back to the video and watch my solutions. So I'm just going to reveal my already filled in solutions here, so we can kind of talk through these briefly. So this first example here, I'm going to let u be the denominator, x cubed plus x. Du then is 3x squared plus 1, which is amazing because that's the numerator. And so I end up with an integral of 1 over u du. You know, now that I'm looking at it, I wrote dx equals du over 3x squared plus 1. That's another way of kind of using u substitution, is to set dx, or solve for dx on one side. So you think about this whole thing as being plugged in for dx. But in any case, we end up with this. We plug the x cubed plus x back in at the end. In the second question, a little bit more complicated here. U is x minus 1, du is dx, and x is u plus 1. Okay, so that's important for this question because we don't have any way of getting rid of the numerator. So an alternative way to get rid of the numerator or any extra x in your question is to solve the u equation for x instead. So if u equals x minus 1, x equals u plus 1, and you're going to plug u plus 1 in for every x and then solve. And this is what you end up with here. We're going to yeah, let me know if you have questions on that, but I'm not going to read through the entire thing. If u is 5x minus 4 in this next example, du is 5 dx, and you end up with 2/5 of natural log of 11. And here are the last 3 examples. All right, so in the first one, then u is actually natural log of x plus 1, which is a little bit backwards, but that's because the derivative then is 1 over x. So that actually gets rid of the denominator that way. So that's an alternative way to do that one. When the denominator is just x and the numerator has natural log in it, that's usually a sign that you want to do it that way. So these two have answers of 15/4 and 31 over 5. And then for the last one, our denominator is not x, so we need to make that our u. And again, we are going to substitute in u minus 2 for x in the numerator to get rid of the numerator. And we end up with -3/2 plus natural log of 2/5. Notice here that we had natural log of 2 minus natural log of 5, which is how we get the natural log of 2 over 5. Okay? So that is the end of the notes. Please let me know if you have questions. I know I sped through the last couple examples, but I'm happy to help in more detail if necessary. Thank you so much for watching, and I hope that you have a great day.